So I sent a mid-semester review after our last class. I think this is what our department recommends for the new faculties, because I just joined last year and this is the second time I'm opening this class. So any feedback is highly appreciated. I don't think that's a very long survey. So I would say maybe after this class, you can spend some time to go through the questions and then just leave some comments, right? No matter whether it's good or bad, right? If you don't like it, right? So I think the major comment I got from our last year was that people were complaining the term projects are too close to the presentation. So basically, for last year, the sulfur dioxide was taught maybe in the last month of the whole semester. So some students were feeling that they don't have enough time to go through the contents. So this year we're moving the sulfur oxides or nitrogen oxides to earlier of the semester. So I hope this can give you guys more time to work on the project. So I also got some feedback from from a few groups about calculating the flue gas flow rate. And so I think it will be easier if you can send me the Excel sheet if you want me to provide some comments, just to have a, like, let's say a sanity check on whether the numbers make sense. You can start to contact me about this. Okay, I can probably help you find out what might be the problem if you just send me the Excel sheets, right? So I think now we got to the time and then we should get started. So from this class, we're going to learn basically the last type of the air pollutant in this whole semester. So that is the volatile organic compounds. So if you notice, actually in the introduction class, when we talk about the criteria air pollutants, we mentioned that is basically PM, right? Sulfur dioxide, nitrogen dioxide, and then we mentioned there's ozone, lead, and CO, right? So we also mentioned that the VOC is not one of the criteria air pollutant, mainly because there are just so many of them, right? It's difficult to regulate each of them or all of them. So in this class, we're not going to deal with these three because these are relatively easy to deal with. So we're going to spend some effort on the VOC control. So mainly because they're also emitted in a large quantity. We're not talking about a specific type of the VOC, but in the overall emission of the VOC, they're emitted in a large quantity and it will cause some health impacts, okay? So if we do a recap of our last class, we mentioned, briefly went through the carbon dioxide control. So we mentioned that if we want to evaluate what is the carbon emission per year, the correct unit we should use is around gigatons, right? And then for the carbon dioxide control, since right now everything is still pretty early, because there are no industrial scale carbon dioxide capture systems. So basically it's a research field that's proposing we can do carbon dioxide control with pre-combustion, in-combustion, and post-combustion method. Okay, it can cover all the different methods we can use to remove these gas species. Okay, and so for this class, first we want to introduce what are the VOCs, what more specifically, what are the vapors? So whenever we talk about the gas pollutants, let's say carbon monoxide, nitrogen oxide, sulfur oxides, ozone, or volatile organic compounds. So it's quite funny how we determine which term we decide to call them. So let's say both gas and vapor are basically the same thing. They exist in the gas phase. But if we talk about, let's say, oxygen or nitrogen, what we call them are typically gas, right? We'll say they're gas molecules. But when we talk about water or ethanol, I think more likely we'll not call them as gas, but we'll call them as vapors. So there are some differences it seems that there are some differences between gases and vapors. And generally for the volatile organic compounds, we'll call them as vapors, right, instead of gas. But for carbon monoxide, nitrogen oxides, sulfur oxides, or ozone, we call them as gas species. So the reason behind this is we generally call a species in its vapor form when it's close to its phase transition. Okay. So for example, for water, we know that it's quite easy to condense water. We just need to lower the temperature, right? And then it can condense onto the surface and form the liquid. And the same for the ethanol. Under normal temperature, room temperature, ethanol is in its liquid form, but it's also generating a lot of vapors because basically they're close to their boiling point, right? And that's why for these species that are close to the phase transition points, we call them as vapors. So since we mentioned about vapors, one important parameter associated with these gas species or vapor species is the vapor pressure. Okay, and people also call them as the saturation vapor pressure. So these two are the same. Vapor pressure. So what this saturation vapor pressure means is, let's imagine that we have a small chamber. Okay, and then we put some liquid inside. This can be water, ethanol, other alcohol as well, right? So the vapor pressure is basically the pressure exerted by a pure component vapor in equilibrium with a flat surface of its pure component liquid at certain temperature. Okay, so basically it's a pressure existing in these vapors when these vapor molecules are in equilibrium with its liquid. Okay, so for example, if we're talking about water, okay, so we have water in the liquid form, water in the gas form. What we know is that under equilibrium, what happens is these water vapors, these water molecules in the liquid form, they're trying to get vaporized into the gas phase, right? And at the same time, the gas vapors are trying to condense into the liquid form. And because of this exchange here, they're in equilibrium. Okay, and then at this situation, the pressure that's existing in this gas form, or in this gas species, is called the saturation vapor pressure or the vapor pressure. And typically we'll use the parameter PVI as the symbol for the vapor pressure. Okay. So then I have a question. What is the vapor pressure of water at 100 Celsius, 100 degrees Celsius? I'm going to launch a polling. And you can answer this question. Just think about the situation when we boil water with our kettle or with a pot. So what is the saturation vapor pressure of water at 100 Celsius degree? Okay, 5 more seconds. All right, we'll stop here. Okay, so it should be 1 atmosphere, right? It is quite easy to understand because if you just imagine that we're boiling water with a pot, okay? And normally we'll put a lid on top of it. And then if we fill water with this pot under 100 Celsius degree, basically we're boiling this water, right? It's at this boiling point. when it's at boiling point, what we can see is the lid is trying to pop out, right? What that means is the pressure inside the pot is actually equal to the pressure outside, right? And because of that, it means that basically the vapor pressure of the water at this temperature is going to be equal to the 1 atmosphere, right? So that's quite straightforward to understand. So regarding the vapor pressure, there's one thing that we may get confused with, which is the partial pressure. So we introduce the partial pressure when we talk about the ideal gas law. For example, we can talk about the partial pressure of water under certain temperature or under certain pressure. So there are some differences between these two quantities. So what the vapor pressure means is the maximum pressure of a substance. For example, for water, under a temperature of, for example, for water, under temperature of around 25 Celsius, okay? So the vapor pressure or the saturation vapor pressure in water is around 0.03 atmosphere, okay? So this is the maximum vapor pressure or maximum partial pressure, the maximum partial pressure that the water can have under this temperature. So the partial pressure can take any value below this vapor pressure and 0. So basically, what this means is the PI can take any value between 0 and PVI. Okay, so under the equilibrium condition, there's no way that the partial pressure of a substance is going to be higher than the vapor pressure of this species. Okay, so this also makes sense when we're talking about the relative humidity, because the relative humidity is just calculated by the partial pressure of water divided by the vapor pressure of the water. Okay, so that's why this RH always have to take values between 0 and 100%. Okay? If it's 0%, that means the partial pressure of water is equal to 0. If RH is equal to 100%, that means the vapor pressure is equal to the partial pressure. Okay. So basically, this is how we can differentiate these two parameters. So the vapor pressure is going to be a constant at certain temperature and certain pressure. Okay, but the partial pressure can be anything basically above 0 and below this this vapor pressure here. So actually, it was quite funny that before I moved to Rolla, I was on Long Island for some time, and if you live by the ocean, normally what you can experience is it's going to be very humid. Sometimes, since I'm living in a half basement in there, sometimes I will just use the thermometer or the humidity monitor inside my apartment. Sometimes when I come back home, I can see the RH during the daytime can be almost 99%. Okay, so this is because the water or basically the partial pressure at the nearby the ocean are going to be brought into, let's say, another region there. If that region has a lower temperature, then the RH will become higher. So basically, the lower temperature region is going to have a lower vapor pressure. Okay, so that's going to lead or bring a very high RH in certain regions. Okay. So here I'm also showing a recirculation pattern of the air, let's say nearby a water, nearby, let's say lake or ocean, anything, right? So this is generally what happens during the daytime. Okay, so what you can see is that the air is going to get recirculated from the ocean and then brought to the land surface, right? And then we know that basically when the air goes over the water, it's going to pick up the water vapor, right? And then if we consider which region has the highest RH, then that's going to be this region here. Normally, it's because the temperature here is going to be lower, right? And then we'll also bring a large fraction of the water vapor into this region, okay? And then if we consider the, how do we calculate RH? RH is basically the partial pressure of water divided by the vapor pressure of water, okay? So the partial pressure is high, and at the same time, since normally the water has a lower temperature, okay, if it has a lower temperature, then generally it has a lower vapor pressure, okay? So this will increase the RH over the ocean area, okay? So, and since we mentioned here about the temperature dependence of the vapor pressure, actually people did a lot of characterization about the how does the vapor pressure change as a function of temperature. So this equation is called Antoine's equation. Okay, I can label the name here. Okay, so the Antoine's equation is trying to characterize the vapor pressure of any vapor as a function of temperature. And here the AI, BI, and CI are just constants. Okay, but one thing we need to notice is that the term BI is negative. Okay, so basically, if you consider everything, if everything is positive, then that's going to be something like, let's say, AI minus B prime, BI prime, CI plus T. So under this situation, everything is positive here. So then how does the vapor pressure change as a function of temperature? Okay, so let's see if the temperature increase. Okay, so the term in the denominator is going to increase. And this whole fraction here is going to decrease, right? If the whole fraction decrease, and since this is a negative term, the PVI should increase. Okay, so what this means is that if we increase the temperature, then the vapor pressure is also going to increase, or the saturation vapor pressure is going to increase. So if we come back to this question here, so this is what I mean. Basically, if the air is going over the ocean here, and if the ocean has a lower temperature, what that means is that the PVI is also going to be lower compared to the land area, okay? And then because this vapor pressure decreased, while the partial pressure of the water increased. So then, because of that, we're going to have a higher relative humidity, okay? So this is the basically the process that's happening in this air circulation here. So here you can see that if we have a higher temperature, then the vapor pressure is also higher. And this actually makes sense. If you consider the water, if we go back to this question here, we're saying that at the temperature of 100 Celsius, the vapor pressure of water is equal to 1 atmosphere. Okay. And if the temperature, let's say, is below 100, let's say the temperature is equal to 25 Celsius, I'm labeling here that actually the vapor pressure of water is 0.03 atmosphere. It's never going to be higher than 1 atmosphere, right? If the vapor pressure of the water is higher than 1 atmosphere, then we're going to feel quite differently on our Earth, right? Because we know that the normal temperature is 1 atmosphere, but if the vapor pressure of water and the normal temperature is higher than 1 atmosphere, then people are going to feel more pressure. So that's why there's another way you can think about this. So what that means is the higher the temperature, the higher the vapor pressure. Okay. And here on our textbook, we have a table showing how the vapor pressure changes as a function of temperature. And this is listing a lot of the VOC species. Okay, so you can see there are propane, 1-butane, N-butane, and a lot of these organics here. So you can find each of the volatile species or the organics, how their vapor pressure change as a function of temperature. One thing you should notice is that the unit here are not standard units. It's using the PSI, and also the temperature is using Fahrenheit. And furthermore, you should notice how the axis was arranged. It's not in the linear scale. Okay, so for the y-axis, it's in the log scale, but for the x-axis, it's not the linear scale or the log scale. Okay, so you can use this type of curves to find out what is the vapor pressure or the saturation vapor pressure at any temperature. Okay, so then we can further take a look at the Antoine equation just for water here. All right, so this equation is showing this Antoine equation again, and now everything is for the parameters are positive now. And so what this is showing is that people actually determined these constants in different ranges of the temperatures. For example, from 1 to 99 Celsius, you have this set of parameters. And from 100 to 374 Celsius, you have this set of parameters. And actually, they don't differ by a lot. Okay, so this is for more accurate calculations of the vapor pressure. And also, if you pay attention to the C parameter here, so the C is the temperature in Celsius plus 200 something. Okay, so you can basically regard this, and these parameters are kind of close to 273.15. Okay, so basically you can an approximation for this Antoine equation is just to set it as A minus B divided by temperature in Kelvin. Okay, so normally people also plot in this way to show this relationship between the vapor pressure and the temperature. So if we plot out the relationship between the vapor pressure and the temperature, and here it's basically showing the temperature in Kelvin and the temperature in vapor and also the vapor pressure in kilopascal, and both of them are in linear scale. You can see actually the vapor pressure increased exponentially with the temperature, right? So you see, actually the normal boiling point is just right here, and this is 1 atmosphere, right? One atmosphere is around 101 kilopascal. So we're really talking about a very low pressure here. And then if you further increase the temperature, then the vapor pressure of water can get really high in there. So people also defined, let's say, the triple point or the critical point, which are very important in terms of its phase change. And for a lot of the coal-fired power plants, because coal-fired power plants are using water in the tubes to turn the turbines, right? So that involves the high pressure, high temperature systems. That's why some of the coal-fired power plants are operated under this critical point, or critical condition. And in this way, we can maximize the efficiency from the coal combustion and convert it into electricity. So for the figure on the right, you can tell basically how people are trying to relate this pressure and temperature according to this equation here. Okay, so if we plot out the log of pressure on the y-axis, and then for the x-axis, let's use 1000 divided by temperature in Kelvin. Okay, and then what you're going to see is basically a linear relationship here. And this is mainly because we substitute this term as the x-axis. So it can be 1000 divided by t multiplied by a c parameter, let's say b prime parameter. Okay, and a minus log 10 of p. Okay, so you can see that if we plot it out, then it's going to show this linear relationship, where the log of vapor pressure is going to decrease linearly with the temperature, right? So by showing these two figures, the main message I'm trying to convey is that temperature is going to significantly affect the vapor pressure, right? And then basically, if we increase the temperature, the vapor pressure is going to increase exponentially. okay? So now, if we think about this process, and actually this vapor pressure has a lot of good applications in our daily life. And I think the most important application is actually about the cloud formation. So we mentioned that under the equilibrium condition, the RH have to be below 100% and above 0%. And this is talking about the equilibrium. And we also know that the equilibrium is very difficult to achieve, right? It's going to take a very long time to establish the equilibrium. And what that means is that for some, let's say under some fast processes or transient processes, we can have the situation when the RH is above 1 or above 100%. We normally call this as the supersaturation. Okay, so what this means is that the partial pressure of some species is higher than the saturation vapor pressure of this species. Right, so this is because the equilibrium is very difficult to establish. And then if we're talking about some fast processes, then the supersaturation can happen temporarily. And as a result, what we're going to see is the condensation, okay? And this is quite easy to understand because I think during the chilly winter mornings or autumn mornings, you can normally see fogs, right? And actually the fog is just because the decrease of the surface temperature, right? So if we have a lower temperature, what that means is the water vapor pressure is also going to decrease. But the partial pressure of the water in the atmosphere doesn't change by much, right? So what that means is as the time goes on, if the temperature further decreases, if we calculate the RH, then we have PI divided by PVI. We may get into a situation where the RH is larger than 1. If it's larger than 1, then we're going to form fog, or we're going to form droplets on all the surfaces. For example, the windshields or on our cars, right? So actually this condensation process has a lot of applications. And the most important, I would say that the most important application is the cloud formation. The condensation is purely because of this process of the condensation. That's basically providing a lot of cloud coverage on our Earth and also maintaining our Earth's energy balance, okay? So to demonstrate this cloud formation process, I hope I have some real items to demonstrate in front of the camera, but I think that will make quite a lot of noise. And what we're going to do is we can imagine an experiment and then just watch a short video, okay? And it has very good analogy to the atmospheric cloud formation processes. So let's imagine that we have a plastic bottle. And if you have these objects at your home, you can try these experiments. So let's imagine we have a plastic bottle and we have some water filled at the bottom, okay? This is just under room temperature. And then if you find a bicycle pump and then start to pumping air into this bottle. And then as we pump in more air, what we can tell for sure is that the pressure is going to increase, right? It's like adding pressure into your tires. And then what this also means is that we're doing work to this system here. So we're adding work into the system. And then according to the energy balance, these extra work are going to get converted into temperature, right? So the temperature is going to increase inside this bottle. So if the temperature increases, based on the Antoine equation, what you can think of is temperature increase, then the PVI will increase, right? So the vapor pressure or the saturation vapor pressure will increase. And what that means is that we can basically vaporize all of these water liquid into the bottle here. Basically, we're warming up the bottle and then evaporate these water into the gas phase, right? So what that means is we're going to happen the bring out the evaporation, right? And then we can keep this bottle for some time, right? And then we decide to release the pressure very quickly. Okay, let's say we remove the cap suddenly. So what this means is that the pressure is definitely going to release, right? And then the pressure will quickly come back to one atmosphere. But at the same time, the air inside this plastic bottle is doing work to the outside, right? It does work to the outside. So according to the energy balance, what this means is that the temperature inside the bottle is going to decrease. And if the temperature decreases, we know that vapor pressure is going to decrease, right? And then if we look at the RH, that's Pi divided by PVI. So originally, when we evaporate the water, then we have the relationship that the partial pressure of water vapor is equal to the saturation vapor pressure at this higher temperature, right? And then we know that the saturation vapor pressure at this higher temperature is larger than the saturation vapor pressure at the lower temperature. And then what this means is that we're going to have PVI at high temperature divided by the PVI at low temperature. And this is definitely going to be larger than 1. So if this RH is larger than 1, we're going to see this condensation process. And basically, we're going to see some clouds getting formed in the bottom. Okay. So here I have a video about this process. And actually, this is coming from another class about the atmospheric processes. And I think it's really worth watching. Let me just share this video here. Okay.
Give me a second. Okay, are you ready? Ooh, I made a cloud. Do you want to see something even more cool? What will happen as I do this? Okay, one more time. Everyone always says yes. Okay. Ready? Oh, it didn't work. Give me a sec. Okay. Okay, so we made a cloud. And why am I doing this, apart from just it's fun? Because this is one of the same processes that happens in the atmosphere.
Okay, so I hope this demonstration can help the explanation quite well. Okay, so what we're seeing is that if we're adding in the air, let's say that for the second half of the demonstration, what happens is we already have the clouds inside the bottle, and then we start to pump in the air, right? So basically, we're adding in the pressure. Okay, it goes back to the cycle, right? We're adding in the pressure. We're increasing the temperature in the bottle. And if we have a higher temperature in the bottle, then we have a higher saturation vapor pressure. So if I have a higher saturation vapor pressure, then if we calculate the RH as Pi divided by PVI high temperature, And because the term in the denominator is much larger, right, then we're going to have the RH below 1. If the RH is below 1, then this cloud will get dissipated, right? And then, so the things goes back, right? If we just release the pressure here, we're going to have a lower temperature, and then we're going to form clouds. And this is, as she said, it's the exactly same process in the atmosphere that's forming the clouds. So the brief processes is, let's say this is our ground, right? We're living happily on the ground. And then also because of the on the ground, we have all the oceans and lakes, right? The rivers, water. And then we have these water vapors getting suspended around us. And then we know that under the ground, normally it's at 25 degrees Celsius, right? It's pretty warm condition, ambient condition, right? And then because of this temperature, we'll also have a partial pressure that's established under this 25 Celsius, okay? And we mentioned that this value has to be somewhere below 0.03 atmosphere, but this is already pretty large. And there are some natural processes that are basically moving this air around, okay? So the air in the above can move down, and then also the air at the ground, surface of the ground, can move upwards. And what we know is that temperature at higher altitudes are going to be lower. So let's assume that we reach to a point where the temperature is around 10 Celsius. Okay, so there's a 15 degrees Celsius difference between this altitude and between this location higher above and the ground. Okay, and at the same time, we know that the PVI, the vapor pressure at this location, is lower than the vapor pressure at 25 Celsius. Okay, so basically the term in the denominator, in the RH, so basically the term in the denominator is going to be lower compared to the term in the, compared to the ground, okay? But at the same time, the water partial pressure didn't change when we move the air up, right? It's just only the term in the denominator decreased because the temperature decreased. So at this point, we may get into a situation when the RH is larger than 1. If the RH is larger than 1, we're going to form clouds. Okay, so this is basically the process that's happening in the nature. We're using this condensation process, using this vapor pressure changing process to determine some important phenomena. Okay. So why is it important for air pollution? We can actually use a similar method to remove a lot of the VOCs. We mentioned that for a lot of the VOCs, we call them as vapors. Right? What that means is they're close to their phase change. So we can change the temperature, for example, just to reduce the temperature, right? So for example, if you want to remove the water vapor, easier way is that once it forms clouds, form liquid. If they're in the liquid form, it's much easier to capture them, right? Because they can condense onto the surface and then further get captured. So we can use a similar method for the VOCs. We can reduce the temperature and then just let them condense onto certain surfaces and then get rid of them. So here I have an example problem. It is saying that an airstream is presently at 1 atmosphere and 160 Fahrenheit. This is pretty high temperature. And it contains 40,000 ppm of the toluene, which is one type of VOC, and it's actually quite toxic. So 40,000 ppc, that means 0.04, basically 0.04 atmosphere, right? We're just converting this molar fraction into a real fraction here. That's 4% of the entire air mixture. So it's asking to what temperature must the air be cooled to remove 2/3 of the toluene. So you can think of this process as the transport of the flue gas in a duct. Okay, so at the entrance of the duct, we have certain high temperature. And then at the exit of the duct, we have low temperature. And then because of the change of the temperature, we know that the vapor pressure, toluene, at this low pressure is going to be smaller than the vapor pressure at this high temperature here. Okay. And then basically by condensing these extra amount of toluene, we can remove these VOCs from the gas stream. Okay. So how do we solve this problem? So first, what we need to do is we have to see whether the toluene is saturated under this temperature here. So the general method we can use is basically by relying on this graph here. So you can see that on this graph, you have the curves for all different types of VOCs. And then it also, if you look more carefully, it also lists the Antoine's equation, or the vapor pressure dependence on the temperature for toluene here. Okay. So what this means is that, let's say we're trying to cool down the temperature. By cooling down the temperature, we're basically moving along the line that's on the x-axis. Right? We're going this way. We're going this way until we hit to this point. We hit to the point that's along this line. And then after that, if we further cool down the temperature, then the air mixture only can go around this way, can go through this way. Okay, so the reason behind that is if the air is further across this point, then what that means is that the vapor pressure of the, let's say the toluene, is going to be higher than the saturation vapor pressure. Or the particle pressure of the toluene is going to be higher than the saturation vapor pressure of the toluene. So what that means is this extra amount of the toluene will have to get condensed onto the into the liquid form. Okay. So because of this mechanism, what we can imagine is that let's say if we do this process again. So let's see, for example, right now let's assume that the original state is in this original state of the toluene at this point. It has certain partial pressure and certain temperature. Okay. And then if we cool down the temperature, it's going to follow this way, because if there's no condensation, then the partial pressure of the toluene is not going to change at all, right? And then it's going to go this way for some time, and then until it hits this line here, which establishes the relationship between the vapor pressure and the temperature. And then after that, if we further cool down the temperature, it can only follow this line here. Okay. And then by reducing this vapor pressure, so basically the extra amount of the toluene are getting removed due to the condensation. All right. So now if we look at this process, then we can first find out where we're at this initial point. Okay, so we mentioned that the airstream is currently at 1 atmosphere and 160 Fahrenheit. So we know that the temperature is somewhere here. Okay, now we just need to find out what is the partial pressure of the toluene. And then you can see that the partial pressure, we mentioned that is 0.04 atmosphere, right? And we need to plot it out on this figure. But right now the figure for the y-axis is in the PSI. So we need to convert the atmosphere into the PSI. And if you do the unit conversion, you can find out that this is actually 1 atmosphere is equal to 14.7 PSI. And then what that means is the PI, or the partial pressure of the toluene, is 0.04 multiplied by 14.7. That is 0.588 PSI. Okay. So if you come to this table here, then what that means is we're initially at this point. okay, somewhere between 0.4 and 0.6, and then the temperature is 160 Fahrenheit, okay. And then if we cool down the temperature and try to remove the toluene, then we mentioned that it's going to first follow this way, and then follow this way here. And where is our ending point? So if we try to remove 2/3 of the toluene, then that means we still have 1/3 of the toluene left in the vapor, in the gas stream, right? So we're looking at a point where there's still 1/3 of its original vapor pressure, or original partial pressure, which is 0.196 psi. Okay, and then we just need to look at where is this 0.196, and you can find out that it's actually in here. Okay, so basically, the final point we're looking at is the point where we have around 0.2 of the psi, and then at a temperature of around 45 to 50 Fahrenheit. Okay, so basically this is going to be a temperature that the air must be cooled down, right, to remove this 2/3 of the toluene vapor. Okay, so if I go through this process again, so this method tries to cool down the temperature of the gas mixture to remove the toluene, right? And then the goal is that we want to remove 2/3 of the toluene from the gas mixture, but we need to first find out how much toluene are there, right? We mentioned that if it's 40,000 ppm, that means the partial pressure of the toluene is 0.04 atmosphere. And if we convert it into psi, that's 0.588 psi. And if it removes 2/3 of the toluene, then we have 1/3 left. So this is the partial pressure and also the vapor pressure of the toluene under this cooled condition for the gas mixture. And if you calculate that, that's 0.196 psi, right? And then basically we're looking for the temperature that's corresponding to this vapor pressure here. And if we look at this table here, we just find out the toluene first, and then find out the vapor pressure corresponding to around 0.2, and this is the temperature we're looking at. Okay, so I hope this process is clear enough. You can also go through the textbook to get more explanations if you're still unclear about this procedure. Okay, so basically we're using this condensation method, which is a process that's happening every day in our daily life, to remove the volatile organic compounds in the gas stream. And this is, I would say, this is a passive method. So it's similar to the gravity settler or the settling chamber. So it's similar to the settling chamber system we're talking about, right? So we mentioned that for the settling chamber, the particles are going to naturally fall down because of their gravity. And the same for this condensation process in the chamber, because we know that the flue gas, the temperature is going to, let's say the condensation. Because we know that the temperature is going to naturally cool down, right? Temperature cools down, then we have the condensation taking place in this chamber here. And then we can remove the VOCs from the system, right? So this is a passive method, and there are more active methods that we can go through as we further talk about these VOCs here. We can design absorbers, we can design scrubbers to remove the VOCs, similar to the sulfur dioxide or nitrogen oxides. Okay, so that's all for the contents of this class. And let me know if you have any questions about this calculations here. And I'll see you on Friday.